Okay, so sometimes when you rotate regions, you get something that's not completely filled in. You're gonna get a 3D shape that's not completely filled in, and the slices aren't gonna be discs. They're gonna look like washers. So it's like a disc with a hole in the middle. But let's look at an example. Okay, so we're gonna take a region that's bounded by the line y equals x, and then the curve y equals square root of x. We're going to rotate about the x-axis. All right, let's draw a sketch of our region. So y equals x is like this. Radical x is like this. And then here's our region. All right, now we're going to want to know where these two lines intersect. In other words, we're going to want to know this point here and this point here. All right, so that point there, just how I drew is, you probably can tell is 0, 0. But let's see how we get that other point. Okay, so again, if you want to tell where two graphs intersect, you just take their equations and set them equal to each other. So we want to know, when does x equal radical x? We can square both sides. Then we get x squared is equal to x. Okay, we can set equal to 0, factor, and then we get the two solutions. X is either 0 or 1. Okay, so 0, 0, that's what we found was down here. And then the other point then must be 1, 1. So the x value is 1. You substitute that into either equation, and you also get 1. So 2 points, a region is bounded by the 2 points 0, 0, and 1, 1. The region is in between those 2 points. Okay, now let's sketch our solid. We're rotating around the x-axis. So draw our graph. Okay, so we'll draw the region up here. And now we draw the mirror image below the x-axis. Looks kind of like Pac-Man. All right, now we see when we revolve this around the x-axis, this middle part's not filled in. So it looks like a bowl. It's kind of like a bowl shape. So really, if we wanted to, we'd make these dotted lines to kind of emphasize that. And now when we take a vertical slice, it's going to look like a washer. And there we go. So our vertical slices look like washers. All right, now we can't use the same formula because we now have washers instead of discs. And if we use disc, we would be calculating too much volume, because that would calculate the volume that's in between. That would calculate this volume in here, and we know that there isn't any material there. So we need we need to change up the formula just a little bit. We still have a horizontal axis of rotation, so we're gonna have dx, so everything's gonna be in terms of x's. Okay, so how we can do this is we have two different radii. All right, so we have a large radius and a smaller radius. All right, so we have a radius that goes from the axis of rotation to the first curve. Then we have a radius that goes from the axis of rotation to the top curve. So we have two different radii. Okay, so we're going to use capital R of x for the large radius. And then a lowercase r of x for the smaller radius. Okay, and again, you can always, the radius is always going to be, the absolute value of the axis of rotation minus the curve. Here, the axis of rotation is just 0. So it's really, it ends up, the length of these radii end up just being the curves themselves. So, in other words, the large radius from here to here, that's radical x. And then the small radius from here to here, that is just x, right? That distance ends up being x, that length. All right, so now we just need to take our formula for the washer method, which is v equals pi integral from a to b of capital R of x squared minus lowercase r of x squared dx. Okay, so like we said, everything is still in terms of x's, because we have a horizontal axis of rotation, so that part doesn't change between disk and washer method. What does change is we have two different radii. Okay, and we said those two radii were, let's see, the big radius we said was given by radical x, and then the smaller radius was given by just x. We're taking dx. Now, to figure out the bounds, that's just 0 and 1, right? Because the x values range between 0 and 1. All right, so then you set up that integral. And now when you evaluate it, check that you get, I'll leave it up to you to evaluate it, and check that you should get pi over 6.